Uh, Before I start to talk about cachalots, I need to give you some context. And let's start from SMT solvers. And the first question is, what is SMT solver? And raise your hand if you have an idea what is it. Yeah, someone knows. So, yeah, in short, SMT solver is a tool that checks that helps to find the solution for logical formulas. For example, we can declare some constants, for example, integer constants, and then we can state some assertions, some predicates that should be satisfied. And the SMT solver can give us a model with the concrete values that satisfies all of the stated assertions, or if there is no solutions, it can tell us that is unsatisfiable formula. And what is an unsat core? Unsat core is a subset of these constraints that give us a reason why this formula is unsatisfiable. For example, back into the previous one, we can SMT solver can give us an unsat core where x greater than 5 and x less than 3. And it's less than the original formula because it just drops the last statement. And this feature is quite useful for the algorithm, but the next what I want to tell about is symbolic execution. Symbolic execution is a program analysis technique that tries to represent the programs as some set of logical formulas, and then we can analyze these logical formulas using SMT solvers, for example. And how it represents the programs. Imagine we have a function foo that consists of 3 if statements, and here we have possible 8 path executions. For example, the first one, the execution when all statements are true. And we can use SMT solvers to understand which of these path executions are feasible and infeasible. And moreover, we can get concrete values to, for example, generate tests or something else. And here we have a problem that symbolic execution has some limitations. And one of the problems called path explosion. For example, we can put this function in the loop, and the number of path executions will increase exponentially with increasing the number of iterations. And that means that we need to use SMT solvers a lot, and that is a problem because SMT solvers are quite resource intensive. And that is why people are trying to solve this problem by reducing the number of calls of SMT solver. And one of the technique is just caching. What is an idea of caching? If we look at the formulas that's produced by symbolic execution, we can notice that that formulas are quite similar. But what does mean similar here? And so the similarity gives us some information about the formulas, the common information probably that we can reuse between the formulas. For example, if we focus on the reusing unsatisfiable formulas, unsatisfiable results, we can use some which information we can use to understand to predict the next results of SMT solvers without using them. There is a state-of-art solution called Utopia that tries to that shows us how we can reuse some satisfiable results. For example, we can compute on SAT-core using SMT solvers, and then we can notice that the seventh formula subsumes the unsat core, which means that the seventh formula is unsatisfiable because it subsumes unsatisfiable formula. And we understood it without using SMT solvers for solving the seventh formula directly, and reduce the number of SMT solvers calls. And how the algorithm looks like generally. The first step is to find candidates like unsat cores that we want to try to reuse. For example, we can get all unsat cores that we have produced during the symbolic execution, and then test each candidate whether it subsumes the candidate. It is subsumed by the candidate, by the formula that we want to check. Okay. It's quite a long operation, so we want to reduce the number of candidates which we want to test, but we also don't want to miss good candidates. It means that we don't want to miss solutions if there are any. And how it can be reached? And Utopia suggests using hash functions to try to reduce the number of candidates. So the first step is, let's compute some hash function for each clause of the candidate and the formula. And at this point, we can try to check the subsumption using only hashes here, but it's also quite a long operation. And what we can do else? We can apply the Bloom filter here. The Bloom filter is a modification of hash functions, a set of hash functions that's trying to map the set of hashes to the bit vector. The first step for the Bloom filter is we should choose the size of the Bloom filter. For example, we can choose 4 here, and then based on computed hashes, we can calculate indices, like just get modulus by size. And then we can set ones to the bit vectors and retrieve one bit vector that represents a formula. And after this, checking the subsumption of the bit vectors is quite a simple operation. It's just literally one operation over the bit vectors, and that is quite fast enough. But unfortunately, of course, we lose information about formulas here, and we can add some bad candidates that are not suitable for testing. That means that the testing of the candidate and the formula will give us a negative result. So we after we will sort the candidates and filter out them, we should apply testing function by checking the subsumption of the formula itself without any hash functions. And here we can continue to the cachalot. And what's the problem with the Utopia approach? For example, we can have a function bar that has 2 calls of foo function with different parameters. And here we have a problem because we have different formulas, but and the difference lies in just different names. But the meaning of these formulas are similar, and it's obvious to human that we can try to reuse the results from the first call to do the second call, and but Utopia approach just fails here to share information between these calls. And how we can improve this algorithm? We can upgrade the Utopia stencilling part considering substitutions. But considering substitutions, what does it mean? It means that we should try to find substitution that transforms candidate unsat core to that form that's subsumed by the formula. And there is the idea how to simplify this operation. The idea is simple. Let's try to, instead of computing the whole substitution for the candidate, let's try to compute the small ones. They are called unifying substitutions, and it's quite simple to compute them because we can just take the clause, the pair of clauses, and check and traverse these clauses and find the needed substitutions in linear time. And after that, we can try to build a common substitution for the whole candidate. How we can do this? What should we do? For each clause from the candidate after applying the resulting substitution should be present in the final formula. So each clause in the candidate should has one substitution. We should choose one unifying substitutions, and these chosen substitutions should be consistent. What does it mean? It means that we cannot take this substitution and this one simultaneously, because x1 cannot be mapped to two different variables at the same time. But what we can do, we can choose this one and the last one. And they are consistent, which means they are not in contradiction between each other. And how to do this? How to do this efficiently? And it seems like not so easy operation. Let's look at the more interesting example. Here we have a candidate that compares variables like a cycle and the function that do the same stuff, but we add also one more clause that compares just to random just to random variables. So let's follow the algorithm. We can compute unifying substitution for each pair of clauses, and then for each line, we should choose one substitution, and all substitutions should be consistent, right? And for example, we can choose this one. And why they are consistent? Because every variable maps consistently to the same variable. But it's still questionable how to do this efficiently. And let's look at this in another way. Let's build for each line or in this table a new table. For example, we can build a table that represents set of the substitutions. yeah, like it's easy to understand what means each row, but yeah, each row means that we coded here a unifying substitution that easily can be translated into substitution form. Well, yeah, I guess that's pretty understandable. But what is consistency in such terms? If we have two substitutions, so two rows in two tables, these substitutions are consistent if their values on the same columns are equal. And in case of we should find all possible substitutions, all possible combinations that give us a consistent substitution, we can apply joint operation over the tables. Joint operation, it is literally do the stuff that we want. It computes it just takes all pairs between the tables and filter out those who are not consistent. So that is why after computing joins over all tables, we will receive substitutions that transforms the candidate to the form where this candidate is subsumed by the formula. In short, we retrieve here all possible substitutions that makes possible a subsumption. Yeah, and how looks like the algorithm now? The first step is computing and unifying these substitutions for each pair of quotes. And then we can build tables from these substitutions. After that, we can perform joint operations over these tables and check whether the result is empty. And if empty, the test fails. That means there is no substitutions that can transform our candidate to form where it subsumed by the formula. And if it's not an empty, so there is a substitution that transforms the candidate, and we can conclude that the formula isn't set because it subsumes by an unsatisfiable core. And what about results here? We have two benchmarks, client CACs, which are produced by client CACs, symbolic engines. So one thing that I want to note here that CAC's benchmark is more complicated, more complex than click benchmark, and because CACs produces more complex formulas like quantifiers, like arrays, and etc. So, and what we can see here, we can see that that the number of renamings that's needed to improve Utopia in click benchmark is not so much, but on the CACs benchmark we see significant improvement, which means that the considering substitutions is quite important thing in reusing unsatisfiable cores. And it's more obvious, of course, if we look at distributions here. And yeah, but that's not a final question about the cachalot. Is it really efficient? Is it really efficient? Is it outperforms Utopia? Like, of course, it saves some time on reducing the number of calls of SMT solvers, but does it really efficient? Does it? It has, of course, overheads on computing such hard things like join operations, unifying substitutions. It takes time, and it outperforms the utopia ones. And the short answer is no, because we have some problems with performance here. The first, the one of the problem is that we retrieve a lot of out-of-memory exceptions here, and moreover, on some benchmarks, on some cases, it's just impossible to wait to complete the caching. And why this happening? The first reason, because the computer-defined substitutions is not so efficient. We will look further how it looks like, because why it is true, but that's not. But the most valuable reason is that join operation will produce quite large tables. And here we can apply a lot of optimizations, well-known optimizations for join operations, because it's well-known area, like partitioning, like I don't know, like scheduling of join operations. So, but I will talk about the optimization that quite specific for our purposes. And let's state some observations here. The first observation that unifying substitution exists not for all pairs. For example, if we will look at these two clauses, there is no substitution that transforms the first one into the second one. That means that we can try to reduce these such situations somehow. The second observation that joining can produce quite large tables in the middle of computation because of similarity of the formulas and because of structure of unsat core. Like, for example, here we have an unsat core that just compares all the first all variables in the beginning with 0, and then compares the sum with and then state that the sum of these variables should be less than 0. And if while we will perform join operations for the first 3 clauses, we will retrieve quite large tables, because in the program really could be a lot of comparisons like this. But the most meaningful clause here is the last one. That is why the first 2 join operations will produce a large table, but the last one could just reduce it to the empty table. And we should treat such situations somehow. And the third observation, that in the end we want to check the emptiness or non-emptiness of the results. We don't want to compute all possible substitutions that are suitable for our purposes. We just want to know if there one or no. And what we can do here. The first optimization, just let's try to reuse our computed hashes that we compute previously for the PUM filter. And why it works? Because these hashes literally represent a structure of the formula. And if clauses have different hashes, it means that they have different structures. So there is no unifying substitution that transforms one to another. So we can just take pairs only with the same hash. And that will hopefully reduce the number of checking unifying substitutions. The second optimization, we can try to filter out some impossible substitutions in advance. How we can do this? For each variable, we can perform join operation separately. Like, let's take the set of y's here and in another table, and then we should intersect these sets because of consistency. Just that is why. And these operations are quite simpler than join operations for the whole table. And as a result, we will retrieve a set of options that could be produced in the result. And using these sets, we can filter out in advance the rows, the substitutions that are impossible. And in practice, it happens that that will, at the end, we will retrieve an empty set of variables. And what does it mean? It means that we just can say that there is no there is no results in substitutions. As a result, we will receive empty table. And it really can speed up the algorithm. And the last one, optimization, is just like make an iterator over join operations. It will reduce the number of computations because it will reduce the number of computations because we want to compute the result at the end, on only one result at the end. And moreover, it will solve the problem with memory. We won't store all big tables in the middle of computations. We just will store pointers to the original tables, which represents a result. And what's about results of these optimizations? The first optimizations, I will remind, it's about it's about reduction of pair for checking for finding a unifying substitution. So the time reduction is quite good. 31%. Well, yeah. The second one is about reducing the large tables. Is about pre-computing some sets of options for each variable, and it gives us 71% of time reduction. And the third one is iterator, and it reduces not so much, but it's important because it gives us a reduction of memory consumption. And yeah, the part of joining will optimize by 71%. And if we combine all of these optimizations, we will retrieve a good optimization that reduces the overhead by 92%. That makes Cachalot quite efficient. And let's look at the full results, which represent efficiency of the approach. Here we can see that overhead, that the time saved by using Cachalot and Utopia is much greater than overhead that we spend, the time that we spend to perform lookup in the cache. And despite the fact that overhead is increased compared to Utopia, we retrieve quite greater time saved. And this is absolute values. But what about the real efficiency for the unsats, and our algorithm reduced the number, reduced the time consumed to solve formulas, unsatisfiable formulas, by 74% compared to 53 utopias. And that means that Cachalot really outperforms Utopia, and moreover, the reuse ratio also shows that considers some substitutions in reusing some results between the formulas during some analysis, for example, symbolic execution. It's quite valuable and reasonable. So yeah, that's it. Thank you for your attention. Probably someone has questions.
Question. So, like one of the biggest problems you mentioned was on unification. And actually, in our lab, we also have which dedicated quite a lot of time on unification. I mean, mini-Cameron team, have you consulted with them?
The problem is not in unification itself, it was in finding pairs. We just traverses over a lot of combinations of clauses that we should check. And the problem is not in unification itself, is more in finding good candidates to find an unification. That is why the unification itself is quite simple in our case, because we just try to find a substitution that transforms one formula in another, and that is quite simple task, which is not so difficult, and it spends linear time compared to the join operations. It's really small time. Yep. But no.
Mini-Cameron team have something to add?
I think my only question is if the formulas are always this small, like
No,
no,
of course not.
Do you have like more complicated structure?
Yeah, with quantifiers, with some different functions, and so on and so on. Yeah, they could be much more.
But still in linear time.
Yeah. That's just comparing. I don't know.
It's linear time by what?
Because we don't want to change the structure of the formulas. Maybe because of this.
All right. So it's basically you always map one variable into another, or
yes, yes, that's so simple.
Nothing for mini-Cameron to do here.
Yeah. You had a question?
Yeah, a little bit lost of understanding. You say that you make the variable mapping, but in linear time. Linear time of what? Of amount of variable to match, or
of the size of the formula of a clause. Computing.
That you do all the joins linear?
No.
Or
Joins are not so linear. Well, yeah, computing this table, computing each cell in this table is linear time to the formula, to the size of the.
So computing all this table is, I'd say, cubic time.
Cubic time compared to the number, yeah.
Okay.
Related to the number of clauses. Yep.
Okay. My question was, instead of trying to find mappings, have you tried, I don't know, maybe this is something impossible and I just don't know much about Sats clauses, SMT clauses and so on, but have you tried trying Have you tried coming up with something like of a normal form for a clause?
Yeah, that's the part of. Okay, that's a parallel optimization that can improve the caching, and most of the state-of-the-art solutions make such unification, let's say, canonization. And in these variants, we didn't perform such optimizations. To be honest, there are a comparison. To be honest, that the state-of-art solutions also can try to minimize the problem with renamings by canonization. Like, yeah, just they are just trying to somehow unify the form of formulas of the clauses, and then somehow unify in a unified way just rename the variables. But in our work, we compared this effect, and Cachalot just outperforms that if we
So you
make
copy is
this.
one of the state of the art. Okay, that's good. Perhaps it may be possible to combine both your optimization and the
Yes,
optimization.
that's possible.
Perhaps that would bring better results.
Yep. But that's a combination of some different things.
Regarding join operations, you are doing these operations by yourself, to kind of self-written algorithm, or
Yeah, that's the self-written algorithm, because I've tried to use databases here, but it's hard to. There is a moment where we can try to transform to adopt the initial representation form into tables load in the databases, then perform these separations, and then back they to the normal form and so on. So that is
slower?
yes, that's slow, unfortunately.
So your algorithm based on what? Based on hashes, or
Which one?
kind of when joining two tables, you are using hash?
No, I don't use here hashes because. Okay, I use some indexes here to perform this. It's better, but that's an optimization that is well known for join operations. So, yep, I sort these tables before the joining, and then perform join more efficiently. But yep, that is not so valuable here. Yep.
Is the join even the longest part of all the process?
After optimization, no.
Oh, okay.
But theoretically, it's still bottleneck or not?
Theoretically, yeah.
Yeah, theoretically it is.
So am I right that Cachalot works only on the level of like one execution of like symbolic executor, in the sense that like you analyze program, you run it with like Cachalot, then like every results of Cachalot raised.
Yeah, when we conduct our experiments, we use the strategy using of cache within the class analyzing, but we also conduct some experiments to try to use cache across the project, across different classes in one project, and it shows that reusage increased, but the efficiency is lower than the original strategy. Unfortunately, because the lookup is quite long, because there are a lot of unsat cores are generated through the analyzing the whole project, and that is why it became not so efficient. So yeah, if we improve the candidate searching, probably it solves something, but yeah.
But in this sense, it means that there is no reason to have like a giant unified database of unsat cores for all.
Yes, that's true. For now, that's true, but I think that is possible to optimize the lookupping and looking upping. Yeah. So,
So actually, the bottleneck right now is to find a mapping from unsat core to elements in the current.
sorry?
So currently, bottleneck is to find an unsat core which we will be interested in. Actually, we perform joining on every unsat core. Yes.
Not on every unsat core. We filter out using Bloom filter some candidates, and then yes.
So the bottleneck is in joining or in filtering out or where?
It depends on the case of usage. If we want to use, as Anton suggested, the bottleneck will be finding the candidates, because there will be a lot of candidates, and the testing each of them is quite long operation, and yeah.
Is there some filtering of candidates like this is useless, this is not performant to find to preserve something like that, or you preserve all candidates and then
I'm not sure that I understand you correctly.
I mean if you find a new unsat core, it goes into future candidates without any filtering, and it stands here forever.
Yes.
Are there any ideas to remove some cores that are useless or too big to be matched easily?
Oh, that's there is some filtering candidates before, like we don't want to see any big unsat cores because they're quite rare, and so they will increase the time computations, but won't impact on the final results. Yeah, that's reasonable to filter out such candidates, but that's still a bottleneck for a large cache. Probably it can be also can be performed simultaneously, like in parallel, and that's also can help to improve the efficiency for the large type of the cache, but that's still questionable.
Also, is it maybe possible to remove candidates which are not matched for a long time?
Yes, we can apply this. Yeah, here we can apply a lot of different strategies for usual caching. So yeah, that's the future work probably.
It just seems like to implement something similar to a score for region SAT is quite easy to do, and at the same time might be.
I don't know.
I'm not sure.
I'm not sure. I thought about it, but not so long time, because I mostly focused on how to do to find a suitable substitution more efficiently. But I I didn't focus on optimizing the finding the candidates and sorting them out or something like that. So that's would be improvements, the future improvement for such algorithms. Yeah. That's it.
All right. Thank you everyone for the attention.